All right, so today we're going to talk about something pretty wild in the world of AI. It's a new model that's trying to bring together two of the most powerful skills an AI can have, the ability to see and understand the world and the ability to create it. Let's get right into it. And this really gets to the heart of it, the big question we're tackling today. Is it possible for a single AI to not just recognize what's in a picture, but to then turn around and generate a brand new one from scratch, using that very same deep understanding? You know, for us humans, it's all connected, right? The part of your brain that recognizes a cat is deeply tied to the part that can imagine or even try to draw one. But for AI? Nah, it's been a totally different story. Understanding on one side and generation on the other, they've historically been treated like two completely separate jobs. And that split, that separation, is what's led to what you could call AI's two-brain problem. It's a really fundamental issue in how these systems have been built for years. See, for the longest time, the most powerful AI systems have basically used two different brains to look at an image. One is all about the big picture, the main ideas, and the other, it's obsessed with all the tiny little details. So that first brain, let's call it the understanding brain, its whole job is to figure out what it's looking at. It sees a photo and goes, okay, that's a golden retriever, it's sitting in a field of flowers. This is exactly what models like Clip are amazing at. Then you've got the second brain, the generation brain. This one is the artist. It doesn't just see dog, it sees the texture of the fur, the exact shape of every flower petal, how the sunlight hits everything, all the little pixel by pixel details you'd need if you were going to actually draw that picture from scratch. And here's the kicker. This whole two-brain setup, it's not very smart. The AI is literally processing the same image twice, but with two completely different goals. It's clunky, it's complicated, and it's been a huge roadblock to building a truly integrated AI. But what if you didn't need two brains? What if you could merge them into one? Well, that's exactly where the hero of our story comes in, a new model called OpenVision 3. So what is OpenVision 3? It's built from the ground up with a totally different philosophy. It's a single, unified visual encoder. The entire goal is to create just one internal picture, one representation of an image that's so good it can be used for both jobs, understanding and creating. Okay, so how on earth does it do that? How do you actually build one AI brain that can do the work of two specialists? All right, so the process starts by taking the image and running it through something called a VAE encoder. Now, you can basically think of this step as the AI creating a super compressed sketch. It's stripping the image down to its bare bones, just the most critical information. Okay, so you've got this compressed sketch. That sketch then gets fed into what's called a vision transformer, a VIT for short. And this right here is where the real magic happens. The VIT's whole job is to take that simple sketch and from it build one single, super rich, super detailed internal idea of the image. This one unified feature. That's the secret sauce for the whole thing. But wait, how do you train this one brain to be good at two totally different things? Well, it's kind of like giving it two different types of homework assignments. So on one hand, you have what's called the reconstruction branch. This is its art class. The AI's homework is to take that unified idea it created and use it to redraw the original image perfectly. Then, on the other hand, you have the understanding branch. This is like its language arts class. Here, the AI has to learn how to connect that same idea to words, to text descriptions, matching pictures to captions. And this is where things get really cool. The researchers found something totally unexpected. These two skills don't fight each other. They actually help each other. It turns out the better the AI gets at describing a picture, the better it gets at drawing it. And the better it is at drawing, the better it gets at describing. It's this amazing feedback loop. Okay, so that all sounds amazing on paper, right? But it brings us to the most important question. Does it actually work? Can this one-brain approach really compete with the old, specialized, two-brain systems? All right, let's look at the report card. First up, understanding. We're putting OpenVision 3 right up against OpenAI's Clip, which is, a total specialist in this area. And look at these scores. They are neck and neck. On these specific tests, OpenVision 3 is right there with it, sometimes even a tiny bit ahead. Let's call it a draw. But now, let's look at the generation test. And wow, this is where you really see the power of this unified brain. When you use it as the seer for an image generator, OpenVision 3 gets a score of 1.89. The old clip-based way, 2.54. And remember, with this score, lower is way better. That's not a small difference. That is a huge jump in image quality. So, what's the big takeaway here? What does this mean for where AI is headed? Let's zoom out for a second and look at the big picture. Well, for starters, it's way more efficient. We can finally say goodbye to that clunky two-brain system. Second, it proves that seeing and creating aren't separate skills for an AI. They're synergistic. Getting better at one literally makes it better at the other. And finally, and maybe most importantly, this is a massive step towards a more complete, more holistic AI, one that doesn't just see the world, but can actually create in it. And that really just leaves us with one final big question to chew on. As these two fundamental abilities, seeing and creating, keep getting woven together, what happens next? What new incredible things become possible when an AI can finally see the world and create from it, all with a single unified mind? Welcome to The Explainer. So that global race to build the future of science? Well, it just hit a massive plot twist. Today, we're going to break down an incredible new blueprint for America's technological future, and it all comes from a recent analysis by NVIDIA on the National Quantum Initiative. You know, this whole quantum thing, it's not just about building faster computers. We're talking about something that's going to define the future of national security, of economic power. I mean, the nation that masters this technology doesn't just get a head start. It could get to rewrite the rules of the game for decades to come. And here's the crazy part. For years, everybody thought they knew what the path forward was, right? Like the roadmap to quantum supremacy was all laid out. But then, boom. Almost overnight, the entire game changed. All those old plans, totally obsolete. So, what on earth happened? Okay, so to really get why the rules have changed, we've got to go back a little bit. Let's look at how the US jumped into this race to begin with, and why their first strategy was actually working really, really well for a while. So back in 2018, you have the US launching this thing called the National Quantum Initiative, the NQI. And this was a huge deal, a bipartisan effort bringing together government, universities, the private sector, everyone. And you know what? It was a massive success. It took these cool quantum ideas that were just happening in labs and started turning them into the real building blocks for actual scalable quantum computers. But here's the big twist, the real kicker. The NQI was so successful that it basically proved its own strategy was out of date. It's like it ran so fast, it discovered a whole new racetrack. The ground has completely shifted, and that original playbook, yeah, it's not going to be enough to win anymore. And this right here, this captures that huge shift perfectly. See, the old way of thinking, back in 2018, was that quantum and AI were two totally separate things, two different races. The new reality, they're not separate at all. They're two sides of the same coin. The goal is no longer just a better quantum chip. It's about building a whole new class of machine, a hybrid supercomputer where quantum and AI are completely fused together. So what does that actually mean? What does fusing AI and quantum together even unlock? Well, let me tell you, it's way more than just getting more processing power. We are talking about a fundamental revolution in how we do science, period. Yeah, just listen to this quote from Dr. Dario Gil. It's pretty powerful. He's basically saying, we're about to invent the modern version of the telescope or the microscope. Think about that. These new systems aren't just about solving problems we already have, only faster. No, they're about letting us see and understand the world in ways that are just flat out impossible right now. And this is what that new scientific instrument looks like, a quantum GPU supercomputer. Now, this isn't some quantum processor sitting in a corner by itself. It's a single, unified system where your classical GPUs and CPUs are working hand in hand seamlessly with the quantum processing units, the QPUs. That tight integration, that's the secret sauce. That's what makes it a real practical tool for scientists. And get this isn't just some idea on a whiteboard. It's the heart of a real national strategy they're calling the Genesis mission. And the goal is staggering. They want to bring together the best minds in the country to build this thing, and then use it to literally double America's entire R&D output in just 10 years. Wow. Okay, so that sounds amazing, right? But how do you actually build one of these things? I mean, it's a huge engineering challenge. Well, the blueprint actually breaks it down into two core pieces. All right, so according to the plan, it really boils down to two key ingredients. First, you need the bridge. Think of it like a super fast, super stable highway connecting the quantum and classical parts of the computer. This is absolutely essential for stuff like error correction. Then second, you need the platform. This is a single open source programming language, something like NVIDIA's CUDA, that lets pretty much any scientist, not just the quantum physics geniuses, actually use the machine. And this is where you really see why AI is so critical to this whole thing. See, the AI isn't just a sidekick here. It's actively helping the quantum processor work. It's doing the heavy lifting on things like real-time error correction. It's constantly calibrating the hardware. It's even helping us find better quantum algorithms in the first place. They're not just partners, they're inseparable. So when you put all of this together, it leads to one very clear, very urgent conclusion. It's a call to action, really. Congress needs to reauthorize the National Quantum Initiative, but with a totally new mission. A mission that puts this AI and quantum integration right at the very center of the strategy. Okay, so what does that actually mean? If you're in Congress, what do you need to do? Well, this blueprint lays out some really clear recommendations for how to take the NQI from being just about basic research to being about building and deploying these machines at scale. So, the whole proposal really comes down to 5 main things. First, we need to fund what are called quantum digital twins. Basically, these are super powerful simulations that let us design and test quantum hardware and software, which is way faster and cheaper. Second, we need to pour money into the AI infrastructure for error correction. This is the only way we're going to get from today's noisy quantum qubits to the stable logical qubits we actually need. Third, we got to create a central AI plus quantum hub, kind of like a shared workshop where all the best researchers can share tools and data. Fourth, we need to launch some big, ambitious flagship projects, tackling huge real-world problems in chemistry or material science. And finally, number 5, we need to empower groups to figure out what scientifically useful even means. We need clear benchmarks to know if we're actually making progress. And listen, this isn't some maybe someday kind of thing. There is a hard deadline. The U.S. Department of Energy is aiming for 2028. That's the year they want to have a scientifically useful quantum supercomputer up and running. And that means a machine that can solve real problems that even our best supercomputers today can't touch. The clock is absolutely ticking, and there's just no way to hit that target without this new integrated strategy. So, there you have it. The path forward seems pretty clear, doesn't it? This fusion of AI and quantum has totally rewritten the rules of the race for scientific leadership. The blueprint, the plan to build these incredible new tools for discovery, it exists. It's right there on the table. The only question left is the US going to build it? Have you ever felt completely stuck choosing between an AI model that's super powerful but really expensive and one that's cheap but, well, kind of limited? Today, we're diving into a breakthrough that lets you get the best of both worlds. We're going to see how you can teach small, local AI models the skills of their giant, expensive cousins, saving you a ton of time and money in the process. Right, so if you're a developer, you know this dilemma. It's the classic choice. Do I go for the cutting-edge, state-of-the-art model that costs a fortune every time I run it? Or do I stick with a faster, cheaper local model that just can't hack it on the really tough, domain-specific stuff? It always feels like a compromise. But what if it didn't have to be? So here's what we're going to cover. We'll start with that power dilemma, then introduce a really cool new idea called agent skills. We'll meet the tool that makes it all happen, walk through its teacher-student workflow, look at some seriously impressive test results, and then wrap up with why this should matter to you and your projects. Okay, let's kick things off with that fundamental challenge. It really, truly boils down to this constant trade-off between how much a model can do and how much it costs you to get it done. This slide just lays it out perfectly, doesn't it? On one hand, you've got the heavy hitters, the giant state-of-the-art models. Their capabilities are incredible, no doubt, but they come with a hefty price tag, and they can be kind of slow, which is a real pain for repetitive tasks. Then on the other hand, you've got your local models running right on your machine. They're lightning fast, they're free, but they just don't have that deep, specialized knowledge for the hard problems. It really feels like you're stuck between a rock and a hard place. But this is where a new idea enters the picture. It's an idea designed specifically to bridge that gap between power and price. And we're talking about something called agent skills. So, what in the world is an agent skill? Well, think of it like a pre-packaged piece of expertise. It's just a set of instructions and some code, saved as simple files, that you can hand over to an AI model. And just like that, you give the model a brand new, very specific ability that it can use over and over again. You know, the best way to think about it is like a recipe.
Imagine a master chef creates this perfect, super detailed recipe for a really complicated dish. Now, pretty much any decent cook can grab that recipe and, successfully make the dish. An agent skill is exactly that, but for an AI.
So who's our master chef? Well, the tool that actually creates these recipes is a command line tool called Upskill. You can think of it as an AI tutor for your other AIs. This quote right here just nails the whole idea. You use one of those powerful, expensive models just one time to create the skill, to write the recipe. Then you hand that skill off to your cheaper, local models to use for all your day-to-day tasks. It's kind of like a Robin Hood for AI knowledge, right? You take the knowledge from the rich models and give it to the lean, fast ones. All right, so how does Upskill actually pull this off? How does it transfer the knowledge? It uses this beautifully simple process that they call the teacher-student model. It works in 3 simple steps. First, you have the teacher. This is our big, smart model, and you give it a complex problem to solve. As it's working, it leaves behind a trace, which is basically a recording of everything it did. Second, the Upskill tool comes in and takes that trace and distills it down into a reusable skill. That's our lesson. And super importantly, it also creates tests to make sure the lesson is actually correct. And finally, you have the student, which is our smaller model. It gets this new skill, and now it can perform that same complex task all by itself. Now, this all sounds great in theory, but does it actually work in the real world? Let's take a look at a test. The team decided to teach a model how to write CUDA kernels. Now, these are super specialized programs for running on GPUs, and it's a notoriously difficult task for any AI. And the results are, honestly, they're stunning. They took a local model and tested it on this really hard task. On its own, its baseline accuracy was only 40%. Not great. But after they gave it a skill that was created by a more powerful model, its accuracy shot up to 85%. It literally more than doubled its effectiveness on a task it was failing at before. I mean, that's a 45 percentage point jump in accuracy. That is a massive, massive leap in capability. It just goes to show how effective this knowledge transfer really is. But here's the thing. Performance isn't just about getting the right answer. It's also about efficiency. And in the world of AI, efficiency usually boils down to the number of tokens or, pieces of words the model has to process. Fewer tokens means faster results and, more importantly, lower costs. And this is where the evaluation tools in Upskill really shine. Check out this table. It shows 3 different models tested with the exact same skill. A big model like Kini gets a perfect score, but it uses a lot of tokens. And get this, the most powerful model, Opus, is so smart it doesn't even need the skill. The skill actually makes it less efficient. But look at the smaller model, Haiku. It gets an 80% pass rate, which might be perfectly good enough for your needs, but it uses way fewer tokens. This is how you find that perfect sweet spot between cost and performance for whatever you're trying to do. So let's bring this all back home. What does this actually mean for you and the projects that you're working on day to day? Because the applications here are incredibly practical. I mean, just think about the possibilities here. You could teach a simple AI to use your company's complex internal tools and APIs. You could build a whole library of shared skills for your team, so everybody solves the same hard problems in the same correct way. Imagine capturing that tribal knowledge from your most senior developers and turning it into a reusable skill that never gets lost. And like we just saw, you can benchmark different models to find the absolute most cost-effective one for any given job. And you know what the best part is? Getting started couldn't be simpler. It's just one command in your terminal. That's literally all it takes to start creating and deploying your very own agent skills. This really does change the game for how we can use AI. Instead of just being stuck with the out-of-the-box abilities of whatever model we choose, we can now become its teacher. We can shape it. So that leaves one final question for you. What's that one complex, annoying, domain-specific problem you've been banging your head against? What hard problem will you teach your AI first?
All right, let's dive into a massive question in the AI world today. How do we actually build better AI agents? Now, we're not just talking about simple chatbots here. We're talking about systems that can plan, reason, and get things done. And for a while now, the go-to advice for making them better has been, well, a little too simple. You've probably heard this, right? This idea that if you have a complex problem, you just throw more AI agents at it. You get a specialist for this, a specialist for that, and you build this big team of AIs. It makes a certain kind of sense, you know? The idea that performance just gets better and better the more agents you add to the mix.
But what if that's just a rule of thumb, a piece of folklore that could actually be leading us in the completely wrong direction? Well, today, we're going to move past the guesswork. We're going to dig into the real science of how to scale these systems, and it's all based on one of the most incredible experiments ever done on this topic.
To get some real, hard answers, researchers over at Google decided to put this whole theory to the ultimate test. We're talking about a massive, super-controlled experiment designed to figure out once and for all when, and more importantly, why, having multiple agents actually works. And when I say massive, I really mean it. They tested 180 different agent setups, and they didn't just use one model. They ran this across the 3 biggest players in the game, OpenAI's GPT, Google's Gemini, and Anthropic's Claude. So this wasn't some casual weekend project. This was a seriously deep, systematic investigation.
Okay, so first things first. They had to define what they were even testing for. An agentic task isn't your simple question and answer stuff. No, it's something that needs back and forth, that needs to gather info over time, and crucially, it has to be able to change its plan based on new information. Think about doing a complex financial analysis, not just asking, what's the capital of France?
Now this is where it gets really cool. This table shows the different team structures they put to the test. You've got your lone wolf, the single agent. Then you have independent agents who all work alone and just pool the results at the very end. But then you get into the more complex teams. A centralized model with a boss or an orchestrator, a decentralized one where the agents actually debate each other, and a hybrid that mixes both. As you can see, each one has a totally different level of communication and coordination.
So you've got all these setups, all these complex tasks. What did they actually find? Well, this is where that simple more is better idea starts to completely unravel. The results were, frankly, shocking, and it all boils down to the type of problem you're trying to solve.
And this slide right here is the absolute key to understanding everything. Some tasks are parallel. You can break them into little pieces and have different agents work on them all at the same time. Like one analyst looks at revenue, another looks at costs, a third looks at market trends. Easy. But other tasks are sequential. You have to do step A before you can even think about step B. You can't frost the cake before you've baked it, right?
And here it is, the first half of the big reveal. For those tasks you can split up, the parallel ones, having a team of agents was a home run. I mean, the right setup boosted performance by over 80% compared to a single agent. In this case, more is better wasn't just true, it was spectacularly true.
But, and this is one of the biggest buts you'll ever see, for those step-by-step sequential tasks, it was a complete catastrophe. Throwing more agents at the problem didn't just not help, it actively tanked performance, dragging it down by as much as 70%. All the back-and-forth communication and fractured thinking created this cognitive tax that just crippled the whole system. So, the takeaway here is absolutely crucial. There is no single best way to build an AI team. It's not about more agents, it's about the right structure for the right job. The system's design has to be aligned with the task at hand. But performance isn't the only thing that matters, is it? Because in the real world, we don't just need AI to be fast. We need it to be reliable. We need it to be safe. I mean, an error in a medical diagnosis tool or a financial model could be a disaster. And it turns out the way you structure your agents is one of the most powerful safety features you have. The researchers came up with this really important metric they called error amplification. Basically, it measures how a tiny mistake from just one agent can snowball and cascade through the whole system, leading to a final answer that's wildly off base. And just look at this difference. It is staggering. In a system where agents just work on their own and never check in with each other, a single error got amplified more than 17 times. But in a centralized system, with that boss agent, the amplification was cut down to just over 4 times. So why such a huge difference? It's all about that central orchestrator. That boss acts as a quality control checkpoint. It's a bottleneck, but it's a good bottleneck, a validation bottleneck. It catches the mistakes from the worker agents before they can poison the entire well. For building AI we can actually trust, this is a really big deal. Okay, so we know now that the architecture has to match the task for both performance and for safety. But how do you pick the right one without, running your own giant experiment every single time? Well, this is where the research takes its most important step, moving from just observing what happens to actually predicting it. They took all of this incredible data and used it to build a predictive model. It's a tool that can actually look at the characteristics of a brand new task and tell a developer, hey, for this job, you're going to want to use this specific agent architecture. This is a total game changer.
And the crazy part? It works. It works unbelievably well. The model was able to predict the best performing structure for a task with 87% accuracy. This is how we move from folklore and guesswork to a real science of AI system design.
And this isn't magic. The model looks at real measurable things, like can the task be broken down into smaller pieces, its decomposability, how many different tools or APIs does it need to use, and how rigid is that step-by-step order. By quantifying these things, developers can now make smart, data-driven decisions right from the start, instead of just taking a shot in the dark. And all of this leaves us with one final, really fascinating question to chew on. As our base AI models get more and more powerful, this research suggests that raw intelligence just isn't the whole story. The really big breakthroughs might not come from just building smarter models, but from building much smarter systems around them. The future of AI, it seems, isn't just about more intelligence, it's about better design. Thanks for tuning in.